Good evening, good evening, good evening. Please, we'd like to start. We have an action-packed program for tonight, so there's still a chance to go and grab some more food, drinks, and we'll get started with the program. So, everybody's ready? Everybody's good? Good. Yeah, there we go. Let's clap hands. Everybody made it tonight at 5:30 to 6 o'clock this time. It's for you guys. Thanks for making it. So quickly, I'll see if I can manage technology. It's not my forte. There we go. My name is Asaf Benoun. I'm from Ecosystem, and I will be moderating tonight's event and symposium. I will try to be as informal as possible, and hopefully we can go through an action-packed agenda, as I said. So let's see some of the things we're expecting tonight. Aman Hihar from Humber College will be introduced in a second. Will give us some opening remarks. We're going to talk about the current project that is happening right now at Humber College, Project Switch. We're going to hear a little update, and then we're going to move into three fun panels. We can talk a little bit again about the format of those panels, but essentially, I have a lot of questions, but if you have questions in the crowd, I'll be able to run around with microphone and pick up more questions. We have a mixed audience here tonight between students, young professionals, not so young professionals, people who are involved in engineering, in procurement, in construction. So we'd like to hear from all of you. Questions from every direction will be great. So there we go. So the first person to open this evening with opening remarks, please stand, Aman. Aman Hihar, the title is the Associate Director of Engineering, of Energy and Climate Change at Humber. So what it means is that Aman is in charge of the connection between the energy infrastructure at Humber College and also the sustainable and carbon reduction and water reduction in general that it can impact on. So if I kind of mention three things very shortly about Aman is beyond the energy efficiency, Aman was part of the IEMP, the Integrated Energy Master Plan that Humber was involved and now Aman is in charge of executing it, where I would say kind of the crown jewel or the flagship project to really accelerate the next steps is Project Switch, which is also under what Aman is doing. So Aman will give us a few opening remarks before we start with the panels. Please, give him a hand.
Thank you, Asif. I was not expecting such an awesome introduction. Thank you for that. I was just ready to walk right up. Good evening, everybody. Welcome to Humber College. Welcome to our first ever District Energy Symposium. We're really excited. When we opened up registration for this event, we thought it was an interesting topic, that people would be interested in it. And then the registration started coming in and we were blown away. Like we sold out, I think 7 or 8 days ago, which it's kind of unheard of, right? For events, typically the last 48 hours, you're selling tickets right up to when doors open. So we're thrilled with the turnout, and so glad that everybody's here today. We've got an awesome lineup of panelists, as Asif said, speakers, and I'm so excited to share our updates on Project Switch because it's a really, really cool decarbonization project we have underway. But more on all that later. I want to start with a land acknowledgement. Which is customary here at Humber for large gatherings. It's my first time doing one, so bear with me, but I'll do my best. So Humber College is located within the traditional and treaty lands of the Mississaugas of the Credit, known as Etobicoke, the place of the alders. The region is uniquely situated along the Humber River watershed, which historically provided an integral connection for Anishinaabe, Haudenosaunee, and Wyandot peoples between the Ontario Lakeshore and the Georgian Bay and Lake Simcoe regions. So when I think back to when I was learning about Indigenous culture and religion in elementary school, I was probably 9 years old. And one thing I distinctly remember is that it was so cool that they would use every part of the animal when they were hunting, right? Like they'd use the bones for tools, the hair for pillows, and the hides for blankets, and even organs for storage containers. They'd literally use every part of the animal, right? And I think part of it had to do with their culture, right? And that kind of deep connection to Mother Earth, which unfortunately we don't have in Western society. But I also think a lot of it probably had to do with practicality, right? Resources were scarce. I've never hunted a buffalo, but I imagined it was probably a lot of work to take one down, right? And so those things had a lot of value. Connection to today, you know, I've been in the energy industry for 15 years. One of the things that I've observed is that energy is just too cheap, right? It doesn't have value. We waste it, we throw it away like it's nothing. Fortunately, that's changing slowly. And that's essentially the theme for today, right? We want to cut out the waste. So like new technologies are great, they're exciting, but they're expensive, right? Let's try to reuse all of that heat that we're throwing away right now first, because it is valuable. There's challenges with recovering it. We're going to get into that in the panel discussions. But once you unlock that, you can start decarbonizing really cost effectively, right? And I think that's the nut we're all trying to crack, right? We know we have to reduce emissions, but how do we do it? How do we pay for all that capital that we need? So with that, I'm going to first thank all of our panelists for coming and spending time with us today. Thank our partners, Ecosystem, for helping to coordinate the event today. And thank all of you for making time to come out today. And please do stick around for the networking after. We're going to have some more food come out. And, you know, everybody just try to have a good time, okay? Thank you very much.
Thank you so much, Aman. And again, I love the whole theme about waste reduction and how critical it is, and we'll encounter it throughout the entire evening. So before we're going to get into the panel, we want to talk about a little bit about Project Switch. It's not going to be too much, but Project Switch is right now I would say the most visible project in Ontario and probably in Canada, where a campus-wide magnitude, an organization, a college here, is moving an entire infrastructure towards the future and towards the direction of net zero. This is an enormous fit, and the fact that Humber showed such leadership is tremendous, because a lot of people are trying, not a lot of people are succeeding. So the update that we're going to get tonight will be from Annie-Claude Thibeault, who's the project director on the Switch project from Ecosystem. As such, she's looking into the entire magnitude of the project and the construction and getting it done. But also we're going to have with her presenting Alexandre Boutin-Frenette, who is on the engineering side. The ability of construction folks and engineering folks to work together towards a common goal is something that is super important, especially for a project of that magnitude, because it allows to deal with the changes on the ground day to day on a flash, and the design is continuously happening all the way until the project completion. So there we go. I won't yak anymore, but I'm going to let Annie-Claude and Alexandre to talk to us about the project. Thank you. Give him a hand.
I think.
D'abord, I suppose.
Okay. Hello. So I'll start to talk a bit about Ecosystem. So Ecosystem is an energy efficiency company, and was founded 30 years ago. We opened our office in Ontario in the early 2000s, almost 20 years ago. We also have multiple offices in North America, New York, Boston, and Columbus, just to name a few. We do mainly design-build projects with guaranteed savings. Just to name a few, we work in the healthcare system, school board, high ed, and industrial. With the project Switch, we are helping Humber to reach their 2050 zero carbon target. Our project will help them to reduce significantly their GHG emission, their energy usage, and bring some savings. With the project Switch, we are helping, for the two main measure of the Switch project are the steam to hot water conversion and the heat recovery. For the steam to hot water conversion, we will remove Humber's 3 steam boilers and replace them by hot water boilers. By doing so, we will be able to heat their building with a lower temperature, and they will have a more efficient network. For the heat recovery measure, we will be able to recover heat loss from their ventilation system and put it back in their hot water network with the help of heat pumps.
So just to update a bit how it's going right now. So for the students here, probably you've seen us working around, maybe me even with my red shirt around today. So we started the first phase this summer. The red line you're seeing is basically where we have the network running right now. This is a new heating network that is only water. So this is to remove the steam eventually. So what happened this summer is the add-up of new steam boilers water boilers in the central plant, centralization of the new heating network throughout the buildings you've seen on the red lines. And we also added some equipment to sustain the steam that has to remain for a while until it can be all removed. So if you use the cafeteria in the K buildings, that means you've used our equipment basically this summer. What is to come is basically connecting the rest of the buildings all together and adding to what is actually already connected to central plant. We will connect it to the residences eventually. So next summer, basically, we will have the final network connected. We will implement the new heat pump equipment for heat recovery, as Annie was talking about. We will do also big trenching to be able to connect the new the residences to the new network. So if you see big holes in your parking lot, that is normal. And we will also electrify the system to remove as much gas as possible from the building with new electrical equipment. In addition to that, we are using other technologies, let's say, to help optimize the energy savings and reduce the cost as much as possible for that energy. So one big part of that is the optimization through controls in the building by implementation of automatization, And we will also implement the peak shaving technology with the use of big battery to help cutting the cost of everything. That's pretty much it. So I'll let Asaf continue. Thank you.
Thank you, Alex, and thank you, Annie, so much. So we have 3 panels, and those 3 panels actually all touch on some of the things you already heard on the project update. The panels are not specific to Project Switch, they're in general. So we're going to talk today about district energy, we're going to talk about the heat recovery, and we're going to talk about innovations and electrification and batteries. So all this, hopefully, we can put as part of the panel. So before I'm calling the panelists, I just wanted to say, okay, I have a lot of questions. I put questions in, I wrote them down, I'm ready to ask. But I'm happy to kick it off with everyone. But if you guys, anyone wants to just ask a question, put your hands up. I will run over with the microphone, and we'll make it as relevant for you as possible, because I think that's the whole intent. So don't be shy. Also, the panelists, don't be shy. And we're going to have, hopefully, can have some fun here. All right. So I'm going to call the first panelists, starting with Fernando Carou from the city of Toronto. Fernando, where are you? Oh, I see you. Please take your seat. So Fernando's is working at the City of Toronto as the manager of renewable energy and net zero development. What it actually means is that Fernando is accelerating innovation and projects in the City of Toronto in order to create the capacity for others to follow suit. So most recently, Fernando was also involved in one of the more successful and innovative projects, the Waterfront Neighborhood Center, where a heat exchanger was done. It was essentially submerged into Lake Ontario. It won one of the Clean 50 awards. So that kind of innovation or that kind of thinking and how to use everything around you is what Fernando is trying to bring into the mix. Please take your seat. Annie, you're coming back. The next panelist here is Michael Conte from FVB. Michael is one of the, really, we're fortunate to have him here as well, one of the sharpest minds when it comes to district energy. FVB's focus is district energy systems engineering, and having an award-winning panelist like that is a true privilege. So thank you, Mike, for coming. You're probably going to open with the first questions because we need to put the pressure on you. Lastly, Max Jeffrey-Gauthier. Hello, Max. Please join us. Max is a senior project director at Ecosystem, and he's also a pretty sharp mind. And so whereas Michael Conte brings so much, I would say, bench strength on the district energy, Max complements him on the building. The district is leading to buildings. They work together. It's one system. And I've seen actually both of them work on numerous projects together. And that's a magic to see because they both understand each other. So there we go. Let's give this panel a hand. Applause. Thank you. Technically, when you take the microphone, you just need to turn them on. There's a switch there. There we go. And when you don't, you don't. Perfect. All right. So please, if you have questions, jump right in. Michael, are you ready? You're going to set us off. Come on. So for anybody here who's not in the tech world of engineering and construction, in the simplest way, what is district energy? Can you answer that question?
So yeah, what is district energy? I mean, district energy is a lot of things, but I'll try to simplify because I don't know everyone's knowledge in the room. But district energy is the centralization of thermal energy and the distribution of thermal energy to the surrounding community. So whereas buildings would individually heat and cool themselves, like a lot of you live in maybe a condo building that has a furnace or a home that has a furnace and an air conditioner, district energy centralizes those services and that production to a central facility and distributes it to the surrounding community. And why, where, what, and when, there's a lot to discuss there. I'm happy to talk to anyone afterwards. But it enables a lot of different things. Resiliency, it enables decarbonization. It really is a springboard a lot of people like Humber are using. They have a district energy system here. It's providing space heating and cooling to this room we're in right now. It really does, it's a mechanism and a tool for allowing decarbonization, resiliency, and I would say redundancy. Yeah. So I don't know if that answered it, but I'm happy. If anyone wants to come pull me aside later and really get into it, I'd be happy to do it.
Or right now.
I project well.
Yeah.
You do.
Can you explain why North America is so different than Europe? Because, and is it become a utility? Because on a campus, they own all of this. Try to do it across the street in Mississauga, and you have to go to the OEB. So what's the impediment to having more of it in Ontario?
Yeah, it's a great question. I mean, obviously, in places like Europe, particularly Scandinavia, district energy is everywhere. Sweden, Iceland, Norway, they have district energy networks that expand and connect individual homes. Even 90% of these communities are connected to district energy. One of the barriers why North America isn't doing it more, it's really, there's a couple things. It's the strength of the gas industry here in North America. I mean, let's face it, the gas utilities have gas pipes almost everywhere. It's very prominent. It's a very robust industry here. It's not that they're enemies of district energy in any way, but it offers something where decentralized gas producing district energy is a lot easier to do. Whereas in parts of Europe and other parts of the world, they don't have that same gas network there. They can't just connect to the gas that's sitting in the road outside and hook up a furnace. So district energy becomes it could be the only solution to their thermal needs. And then the other part to that is that it's something that is not regulated here either. So your point about, why isn't there just district energy everywhere? Why can't I run a pipe across the street and connect? It's not a regulated market here in Canada. Vancouver's got some regulations. Halifax is working on putting in a couple of regulations right now, but in Toronto, in the rest of Canada, there are no district energy regulations. It's an unregulated market. So
maybe I'll take a question now, since we have Fernando here, and we're speaking about the City of Toronto. How does the City of Toronto sees the evolution of district energy in the city? How do you think, from the city perspective, regulatory or otherwise, you see the future?
Yeah, no, good question, actually. I would say, actually, that in Toronto, actually, in fact, we have, one of the oldest, some of the oldest district energy systems in Canada. And, to tie it back to the discussion earlier, I think, actually, they were developed, for educational, government, and healthcare campuses, when we were using coal, right? So pre-natural gas. So it made actually almost physical sense that you wouldn't be delivering coal to every building, and you would have actually a central facility, and then you can pump water much easier, right? So to tie it back, actually, I think the advent of natural gas, initially from Pittsburgh, and then when we got it from Alberta, right, it was a no-brainer, right? So we invested actually in regulated electricity, and then we invested actually in regulated natural gas. In Scandinavia, my understanding actually is with the oil crisis, they were using actually oil, and they did not have access to natural gas. So they kind of leapfrogged natural gas and went all in for district energy. So this is a bit of a history, right? Now, I have to tell you actually that district energy is really dear to my heart. When I started with the city a little over 10 years ago, and John knows this, actually we started doing, in fact, my title actually was Senior Engineer of District Energy for new systems. So we now saw the imperative of, if we were going to address climate, right, then district energy actually was an excellent tool. So we hired FAB, actually we did an analysis actually throughout the city of where could actually district energy be supported. And it was just on the basis actually of existing density and then new development. And to our surprise, actually there were like 30 plus locations throughout the city where you could actually develop district energy, right? Now the challenge actually, as was said a second ago, actually is it's not regulated. So the issue actually is, aggregating the customer base, negotiating all the agreements. So it's a demand business, not a supply business. When you get a regulated utility, you can actually work on the supply side. You build, the wires, you build, the pipes for natural gas. When it's non-regulated, right, you have to start from the other end, and that makes it extremely difficult. So yesterday, actually, I was in a panel for wastewater, and we had actually the city of Helsinki, and they were talking about actually, hundreds of megawatts of district energy systems, right? Like 1 and 2 orders of magnitude larger than what we have actually in Ontario, right? And so that's actually the reality actually is that by it not being regulated, not being made a choice actually that thermal energy was going to be actually sort of a, that tool, right? Think of it actually as mass transit for energy, right? We sort of are living in this space where we can make, sort of small interventions, right? Even the very iconic successful deep lake water cooling system in Toronto, right? It's small compared to actually European standards, right?
Can you actually talk a little bit about that? Because I'm not sure everybody knows about that.
Okay, so because the comparison is always actually, so we had district energy when we were using coal, made total sense. We went to natural gas, and then what was the point of district energy? It was just complicated to coordinate, right? So then we went to natural gas distribution. Now, in the climate imperative, actually, we're thinking, hey, maybe we should be going back because it makes total sense, right? So going forward, actually, when you look at the most successful sort of, recent last 20 years, deep lake water cooling is an example, right? It's as you may know, actually, obviously Toronto sitting right on the shores of Lake Ontario. Lake Ontario actually is one of the Great Lakes. You have all year round 4-degree water at depth, right? And even then, we are hitting maybe 100 buildings in downtown Toronto, right? So it's a small, it's a big district energy system based on North American standards. It's a very small district energy system based on European standards, right? And again, it's multifactorial. There's actually many reasons for that, historical and otherwise, right? But maybe an oversimplification. But I think that comes back to that where Scandinavia actually addressed the oil crisis, by doing district energy. We never had that moment yet, maybe, right? So the question actually is going forward, if we are going to do district energy, it needs to be, taken on more as a, as a broad solution by other levels of government. Like cities cannot do it alone. We can do deep water cooling. We can do, we're doing wastewater energy to decarbonize, hospital campuses, right? But it will always be a smaller intervention, 1 or 2 orders of magnitude smaller that it could have been, or what you actually compare it with the European style development. Hope that's helpful.
That's very helpful. Yeah. Yes?
A follow-up question. Is this something that Toronto is working with other municipalities in Canada, or is Toronto leading it?
Yeah, so by being, the largest city in Canada, right? And we have a big team. We have about 100 people working only in environment and climate, right? I was just discussing with Michael that, if you look at, even per capita, right? We struggle to work with other cities because they just don't have the personnel, right? So by definition, actually, we tend to do things first, right? But then we're very conscious, actually, that climate actually is more than boundaries for one city, right? So we work actually with our adjoining municipalities actively now, actually, on wastewater because it's becoming, quite active, and every municipality has wastewater, of course. So we're working with Yorke region, Durham region, and also, King County in Seattle, Vancouver, Metro Vancouver, Helsinki, and other cities through the networks that we belong to. So we're mostly interested, obviously, in working with our sister municipalities, especially within the GTHA and beyond. But we're also part actually of networks, like C40 and Carbon Neutral Cities Alliance, right? And we work internationally with them. But it's about actually, we're not competing. We want to cooperate on climate with other jurisdictions.
That's right.
Yes, go. Of course. Yeah, someone had mentioned earlier. I don't need it. Someone had mentioned earlier that the level of density required to make the district energy system viable in the city, and that there was different sites identified for that. What went into that decision-making process in terms of where it might have an application?
So you mentioned the city. I'll start actually. I'm sure Michael can jump in. So it's a very practical, calculation, right? And I'll go back to the deep lake water cooling example, right? So deep lake water cooling actually, it was an investment of $100 million to put new pipes in the lake, okay? And by the way, actually, there was a dual purpose. So Toronto actually was having poor water quality, so we needed the pipes for the water system. But the water department could not actually afford $100 million. So by putting the two problems together, right? If you have a big problem, make it bigger, right? Because you get more scope, right? So the deep lake water cooling system on its own did not work, the business case. The water system on its own did not work, but together actually they worked, right? And this started actually as a City of Toronto agency, N-Wave, right? And then we sold it. But to go back to your question, so imagine actually that, well, what do you need? How many customers do you need, right? To start actually with infrastructure bill of 100 million, right? And that's just the pipes. It's about 300 million when you add actually all this distribution, equipment, and all that, right? So it's almost a necessity, right? So you can equate it to what density do you need for a subway, right? If a subway is going to cost $1 billion per station, right? Can you put it actually in Northern Ontario? Unlikely, right? So that's what I'll say actually, that there's no sort of rule of thumb. Like it's not a cutoff where, if you have this density, that density. Consider actually, maybe last thing I'll say, and I'll let Michael jump in. Consider actually that energy goes one way, cash comes the other way, like money, right? So the question is, how much money do you need to come back for that energy to pay for the capital infrastructure, right? And that's the answer to the scale.
Yeah, nothing further to add. I mean, Fernando kind of covered it there. The only thing I'd add is that when you think of district energy, again, it's the thermal distribution of energy, right? So we talk about the density. Well, if you have to run pipe 10 kilometers to pick up a small customer, yeah, that, like Fernando said, the cost of the pipes in the lake, that's one thing, but you also have to put pipes in the ground to supply the energy. Well, if you can run a pipe 500 meters to pick up 10 megawatts of load versus running it 5 kilometers to pick up 100 kilowatts of load, it's going to cost a lot more money to do it. So you have to, again, what's going out is energy, what's coming back is revenue through energy sales. You need to have higher loads to justify that higher initial capital. There's no getting around it. District energy is a capital-intensive business. It's not something that, it requires a lot of infrastructure. It's an infrastructure project. You're creating a utility. You're creating a business. So you got to put in big money in infrastructure, but you have to have some revenue or something tied to that investment to be able to make it a business.
So we're trying to create here a business. We're trying to establish a network, but the network is feeding buildings. From your perspective, Max, how do you deal, first of all, with historic buildings? Old buildings are already there, so we're now putting a network to buildings that are already existing. From your perspective, how is the integration would work ideally when you're putting a new network, when you already have established buildings, a city is developing, or campus is developing? How do you put it together?
So it's a loaded question, Asaf. So
That's what I do.
yes, thank you. So we talked about district heating, and so historically, especially in North America, and correct me if I'm wrong, but the district energy system that we have are mostly steam distribution and steam fed, right? The other ones, and that's because buildings require roughly so basically what you need to do in the building is to heat the room and stuff like that. So you need 20, 30, 40 degrees Celsius to heat up the buildings. But because everything was built a long time ago, everything was built on steam. So you would produce steam and then send steam through all of the building, and it's convenient because steam just moves through pressure. You don't need to pump it; it just flows in the pipe. So historically, I guess they were building district energy with steam to feed all the building. Now we're facing a climate challenge, an energy cost challenge. That we need to address. And so what do we do with that? Steam is very inefficient. When you produce it, it's really inefficient. To distribute it is also very inefficient because you got a lot of losses and stuff like that through the district and in the building. So a little bit like Annie-Claude was presenting here at Humber, what we're doing is that we're going from so Humber benefits from district energy, all the buildings are connected together. So what we're doing is that we're converting a very high high losses energy district energy system to a lower losses district energy system. So that's what we're building right now, and that's only to improve in the efficiency of energy production and distribution. But what it allows us is then after to use other type of technology that was not convenient before. So right now everything is working on natural gas, but because we've switched from steam to hot water, then we're going to be able to use heat pumps, which is going to make another leap into decarbonization.
That's great. So Annie, we heard here a lot of big ideas, but somebody has to get it done. Somebody actually has to be the boots on the ground to implement the district energy network. From your experience, what are those challenges? Because I think, especially for among new students and seeing professionals that actually move things forward, what do they need to think of? How do you see it from your perspective?
So for the switch project, we're doing the converting the steam to hot water. Is that on?
I'm not sure.
It is, okay. The challenge is the steam. You have a big pipe and you have the condensate pipe that is smaller. And in this project, we are replacing all the steam pipes. So the challenge is to be able to go through all the buildings and have those massive pipes going around the campus. And in this case, here at Humber, there was a few buildings that were not connected to the steam network. So we need to bring pipes on the bridge. I don't know if you saw the first pictures, but so we're crossing a bridge. So that's a challenge. Like it's a big pipes to bring on a bridge. So those are the challenges, the sizes of the pipes for the network that we are making.
That's great.
It's one of the challenges. There's many more, but
I'll take one last question. Yes, go ahead.
Actually, two questions. Looking around, Humber College looks like lots of new buildings. So you probably didn't have any asbestos, so did you?
you're wrong.
A lot of asbestos.
There's not too.
Look in the building. I think you have to clear everyone out.
There's not too much, don't be too concerned, but there will be a bit, so right now we did the phase 1, so it depends of, we are able to remove the asbestos, do the asbestos abatement safely, so we don't need necessarily, we did it, let's say like for the phase 1, it was in the central plant, so we did it during, like nobody can go in the, so there's a, yes. What? Protocol? Yes, protocol. So yes, but yes, there is still some asbestos on the insulation.
But it's mostly on the pipe, so it's not like in the walls, or maybe there is on the wall, but it's mostly on the pipe. So if most of the time it's on the elbows of the pipe and stuff like that. So if you don't touch it, then you're good. But if you need to work on it, then you need to use the protocol.
But here at Humber, this is a newer building. I don't remember the year that this building was built, but there's older buildings that were built, like in the 90s, 50.
I wonder if the panelists could say a little bit more about regulation and deregulation. Michael and Fernando both said it's necessary, but if you look at Scandinavia, you've had a very unregulated environment in Sweden and a very regulated environment in Denmark, and district energy seems to thrive in both places. And if you look in Toronto, going back to the Toronto District Heating Corporation before Enwave, it was the deregulation of natural gas, and I know it's not quite the same thing, but it was the deregulation of natural gas that actually saved that corporation, because through deregulation it was able to get better prices than the buildings could. So I'm a little suspicious of arguments for regulation. I'd appreciate hearing more.
Yeah, I can start on that one. I don't know if it maybe came across that way. I don't know if I don't think I took a I don't think it's important for it to be regulated. I didn't. I actually said that it is a deregulated market. And actually talking to a lot of our clients, a lot of district energy suppliers are actually not upset about that. I mean, it is unregulated. And what that means for a lot of people here is that it's unlike gas and electricity. You know, Enbridge can't just double your gas rates overnight. It's regulated by the government. Electra can't just double your electricity rates. It's all regulated. District energy doesn't have that regulation. So what protects people? Fernando mentioned it, the contracts are important. These are contracts that are signed between a user and a provider. Those provide the protections about raising the prices. And without regulation, this is, one of the things where people that are pro-regulation say, well, we need regulations because we need to force people to connect district energy. It's not going to work if we don't force people to connect. Well, as soon as you talk about forced connections, you have to be regulated. And district energy to date in a lot of areas in Ontario, a lot of the systems that are going now, they survived in an unregulated market because they were competitive. They were cost competitive, and people wanted to sign up to them. They weren't forced to sign up to them. In places like Sweden, and where it's regulated, and the city of Vancouver now has some new regulations, they could actually force and mandate connections to these systems. So I don't think, it's definitely not something that's necessary, in my opinion, at the moment right now. And the industry is, some people are pro-regulation and want regulations. A lot of people who run district energy systems have no interest in it because they're competitive as is, and they're running successful, profitable district energy systems in an unregulated market.
Yeah, Richard, I think it's a really good question. And Michael, thanks for, maybe, can I add a little more? Okay. So maybe, Richard, I think it's a good point you're making. So maybe I'll actually correct what I said earlier, which is to be clearer, it's not about regulation or non-regulation. I think it's about rate base. Okay, so if you have a rate base, means that it's a social enterprise, right? And what that means actually is that there's a social cost to providing the service in a wide area. That's why actually Europe systems are like 10 and 20 times bigger than the ones we're doing in Toronto. By not having a rate base, by having to have contracts with each client, it akens more to like a real estate transaction, rental, right? So then by necessity, actually, each customer actually will want to pay only their way, and there's no socialization of the cost. So to Michael's point earlier, if you have to do a pipe actually for a small load, and it doesn't pay, and that customer doesn't want to pay that, right? Without the rate base, then that connection does not happen, right? So hopefully that's helpful, actually. The better lens actually is rate base, socializing the cost and the investment over a broad area. That brings you much bigger systems, right? Without actually that rate base, then you get into an economic transaction actually where it's only really, where there's density, where there's big loads, right? And it's proximity to each other, right? And that's kind of the scenario that we have actually with district energy. There is no rate base with district energy that I know of in Ontario. Does that help, or? Yeah.
Thank you so much. So this panel did a great job. Thank you very much. We got to move to the next panel, but some people here will stay. So thank you. Thank you, Annie. Thank you, Michael. So session panel number 2. Oops. I'm gonna get this technology thing sorted out one day. We're gonna talk about waste heat recovery in this panel. So the session panelists, we're gonna have Max and Fernando stay here, but we're gonna have a few folks joining. Alex, you're back on the hot seat. But I also wanted to invite Michael Genin from AIR. Where is Michael? So we spoke about the people who do the planning, the people that do the regulation, the engineering, there's construction, but somebody needs to manufacture the equipment. And that's where AIR is coming, producing a lot of the equipment, the HVAC equipment that is being used in such project. And Michael is the founder of the essentially the Canadian operations over here. Is that correct? There we go. So provide some point of view from that perspective. Now, once we have a lot of equipment set up and everything is ready to go, you still have to have a brain on top of it. So equipment needs to operate in the way that it's intended to. And this is where you need to have some smart controls to control the whole system. So I'd like to invite Peter Christiansen from Siemens, who's been doing that for a long, long time. Thank you so much. And so the panel is changing for the topic of heat recovery, because everything needs to be installed and regulated. Again, I'll go first, but then please jump in. So this is an easy one, Max, but we're expecting a good job. What is waste heat recovery?
So waste heat recovery. So basically, it's I'll go simplified, but it's energy that wouldn't be used anymore. So either through a sewer or either through air evacuation. So it's air that it's either contaminated or that's not used anymore, but still has some heat within it. So you could reuse it either with passive means, so by recovering the heat from it, but passively just by heat exchange, or you could use an heat pump to increase its value. So that's the idea.
I'll continue. All right. So, Michael, what are the limitations to the adaptation of heat recovery from a machine's perspective? When people are calling you, they need the machines, what are the limitations? How are you thinking about it when you're starting to think about heat recovery? When you need to provide the equipment, to provide the thought of, how do you start your day on this one?
Sure. I guess to elaborate on what Max said, I assume we're going to talk about, kind of heat recovery within the building or the campus, for example, like this project. Obviously, there's like air heat recovery, which, for ventilation, most people would think of. But in these instances, like kind of Max was alluding to, is, we have some kind of waste heat somewhere in the building or campus, or if it's district energy, maybe in an adjacent building. And we have to move it to a place where it's going to be useful or recover that heat. And, here it's quite cold, and that heat has to be in some useful or a high-grade form for it. So we started the campus, used to be on steam. That's kind of your highest grade form, as steam is very high pressure, very high temperature. And now we're going to hot water, which is a little bit lower grade form. But in other areas, you think of, for example, geothermal. The ground is always 10 Celsius. It's a very, very low-grade form of heat. So we have to upgrade that heat, and that's where potentially something like a heat pump comes in, where we're using a refrigeration cycle. And so the big limitation there is getting the water hot enough to be useful to heat that building. You might have the heat in terms of kilowatts or BTUs, but it's just not at that temperature where it's going to be useful. So, heat pumps here are all using refrigeration, and refrigeration's been around for a very, very long time. Usually you think of it like refrigerator or comfort cooling, but they're never designed to make hot water at the other end or that hot of water. So, there's a lot of new things that are being worked on to get those compressors and refrigeration systems optimized, not looking at the cooling, but on the heating. So those are different compressor technologies, new refrigerants potentially that would make upgrading that heat efficient and more feasible for a broad range of applications.
That's great. Peter, your thoughts, especially when it comes to the controls.
Okay, so my personal experience with controls is within buildings. So this building right here, there's a Siemens wall sensor. It's controlling, I presume, what do we have in here? VAV boxes? I think we do, right? So we have these temperature sensors go back to VAV boxes. Where I've seen applications of heat recovery within buildings, primarily is through things like heat recovery from exhaust. You have buildings like labs and what have you, there's a humongous amount of energy that gets wasted in exhaust. Most jobs that are constructed now The makeup air is coupled with exhaust heat recovery. This is also done for kitchen ventilation systems. I can think of heat recovery on a bigger scale that we do with Siemens industrial controls. So the controls inside a building generally are done with what's called building automation, but the controls at the level back from that in the centralized district energy systems are generally done with PLC systems. So people have talked about the deep lake water cooling system. That's all controlled by Siemens PLCs. There's a job that's starting soon. It's underway right now, and they're going to take heat out of the wastewater from the GE Booth water treatment plant that just conveniently happens to be located next to some prime real estate they're going to turn into a big development in Lakeview in Mississauga. So Siemens is involved with that in recovering all this heat. I mean, think about how much heat would be in wastewater. Lots, right? And it's just all going back into the lake. So the motivation there is to take the energy out of the water that would just flow back into the lake anyways and recapture it and make use of it in that fashion. So there you go.
Maybe to complement that, so in an existing building like this one, so there's already like bunch of systems that are operating and are connected on the district energy system. And so all the, so we discussed the heat recovery through heat pump, but that needs to be synchronized and with the other combustion equipment item. Otherwise, like the boiler, for example, will just produce so much heat that the recovery won't be able to happen. So there's a lot of control system and control point to orchestrate all those equipment together to make sure we maximize the heat recovery and we minimize the combustion of natural gas.
So maybe Alex, with the Project Switch, how do you see the heat recovery being used right now? Or on the construction and the design?
Yeah, being used, basically we are currently, we will use the cooling network to put it back to the new heat pump going in the central plant. So on our end, what it means concretely is like running new pipes on the buildings where there's not right now. So that's what about the trench as an example for the residences. So it's, on our end, it's a big challenge, really physically on ground. Also, there's always the communication in between the equipment, like Maxime was talking about, and mentioning working with Siemens and in hand. And it's not always easy control or like typical stuff. So there's a lot of thinking going into it, a lot of discussion to happen. So, and it's taking a long time to do. So it's a project of 2 years. So there's some phases. So what do we do when we have only parts of the heat recovery possible? What do we do when we have the equipment installed but the control is not there yet? What are the challenges? How much can we still do to help the client achieve heat recovery as much as possible, as quickly as possible, even though nothing is completed yet? So all the things like that.
That's great. We really want to use the entire Buffalo. Go ahead, Max.
It's a bit counterintuitive. So we're building the district heating network, and on the flip side, we're extending also a lot the cooling network, because the intent is to go and cool every sources of heat we can and bring it back to the chiller. So we're cooling even stuff that was like, why are you cooling an exhaust? Well, the intent is just to grab the heat from it and bring it back to the chiller so it can be re-inject into the district heating afterward using the heat pump.
So just to add, as an example, we are currently we will already connected to the server network. So the room is pretty hot. So we are cooling off those rooms, and all the heat goes back to the central plant. So that is already implemented in the building now.
Maybe actually, so really good discussion actually, maybe for the students in the room actually, you may be wondering what is heat recovery or why are we doing this, right? So that energy is not free. So you're paying for 100% of the energy. How much are you using, right? So you have to consider that you're paying for, electricity, whatever it is, to do a function, right? And your choice actually is to exhaust, some of that. Like thermodynamically, you can never get 100% of your energy use. There's always going to be some losses, right? So there's a couple of scenarios actually that are important to highlight that we use in our work. When it's sort of one, let's say a building or a campus all under one ownership, there's a different discussion. The discussion is always, we know there's energy loss, but what's the cost of recovering it, right? And now for environmental reasons, for climate and so on, we can justify putting capital to recover heat, even if that heat actually is less than the energy that would require to buy it, right? So we're doing it actually for efficiency and emission reduction basis, right? The other example actually is when the heat is waste from somebody else, right? So that's the example actually of wastewater. And you can have this actually also in the building itself. You can recover heat from the effluent, of a shower, right? Showers. So you can do it in a home situation, right? You wrap, a coil in the stack actually of the sanitary sewer, discharge, right? And you can recover that heat that you paid for, right? So that's what we're trying to do actually at a large scale. So think of those two sort of scenarios, right? You're recovering heat within, your organization, your home, whatever it is, and the other one actually is trying to pair heat that is being wasted from sewer, from data centers, that can be then redeployed, to avoid actually, using, for example, fossil fuels, right? So this is the importance, right? Again, not trying to lecture here, but the concept actually of the importance of heat recovery and utilization of waste heat. Hope that's helpful.
Question, Fernando. Toronto Water has a nice map on its website showing how much heat you can get from many different points in their sewer system. And do you know how much heat in total you could get out of Toronto's sewer system?
Absolutely, yeah, because we did that work actually. So we have in Toronto actually, we launched the wastewater energy program. So my department and Environment and Climate were the front office facing, so we developed that map in cooperation with Toronto Water. So Toronto actually has 3 wastewater treatment plants. And then the network actually is basically almost like a tree, right, that leads to the treatment plant. So if you add up all those quote-unquote sewer sheds, you get into upwards of 300 megawatts of thermal energy.
Sorry?
300.
300.
And that's only from the from the larger sewers. So, but it's about 300, and you can Google this actually. Like the report actually is public. And in fact, actually, not only we have a map that shows the calculation, we have an interactive map on the website where you can put your address in Toronto and it will show you the closest connection to sewer. And it will show you the flow and the temperature there. So there's a self-serve step to screen your project in or out. So if you decide actually that the resource is close by and it's at the right scale, then you can submit a proposal actually to my office, and we review actually then the concept design. There's an agreement, right, that you can enter into. So connecting to the sewer for heat recovery is similar to actually connecting solar to the grid, right? So the city has made a decision actually that we wouldn't get in the business of building these systems. What we would do actually is get in the business actually of hosting the connection and making the energy available.
Yeah, I'm interested in at Humber College. What size of district energy system is it about in terms of cooling or in heating in megawatts. What kind of temperatures are you moving to now that you're going to water instead of steam? And what kind of COPs would you be looking at with the heating COPs with the heat pumps?
So I don't remember exactly the numbers of megawatts in heat recovery. Maybe my colleague at the table knows by on top of their head. But I know the network is supposed to be maintained around maximum 160 Fahrenheit. Return around, let's say, 140. So delta T of 20 Fahrenheit. And what was the last part of the question, sorry? That I'd say, do you know by hand?
The heating network is around about 20 million BTUs for all the network. Hello? Okay. And temperature operation temperature will be at the maximum under 75.
Yeah.
Under 70, this is the maximum, the peak. And we expect to have a return around 130. And the COP will depend on the temperature of the return at the end, and it will vary with the load on the building and the load of outside, the load of the temperature of the network. And we expect, I don't have the number in my head, but it would be around 3 of COP for the heat pump.
Thank you. Go all the way to the other side.
It's funny, we're always talking in megawatt and everything, but all the industry is still in BTU and Fahrenheit, so it's hard to...
Canadian.
So I guess I had a question for Alexandre. You had said that you were looking to do some peak savings, and that was going to bring that back into a battery bank that you guys had. And I was just wondering what sort of decisions or how you guys were making decisions as to what got turned on, what got left off as you're doing some of that peak savings, and then, how was the heat recovery kind of affected as you're turning and setting stuff back?
Yeah, so the peak saving, basically you try to cut as much as possible with keeping all the heating that you absolutely required working. So on our end, basically we are cutting off anything that is regarding humidification. We're cutting off as much as we can of heating, of course. And I'd say anything, I guess, that would be according to ventilation, things like that. You want to be as less, like the more economical possible electricity-wise. So that's pretty much it for like on our end. We were mainly working to cut down the humidification, I'd say. Yeah, that was the main part of it. But I know that Humber is already implementing peak shaving on other things that we ecosystem are not working on. So I don't know the full extent of it, but obviously there's a lot of other things. And this is actually a project that they are implementing with Siemens. So, yeah.
Maybe I can add some more information that, as Alex told, Humber is already doing a pretty good job to do peak shaving with the GA event, and are able to cut a lot of peak during this period of time. And the batteries will be used during the GA time to reduce them. They expect to use an external firm that will do prediction of when this will happen. And the battery are able to provide 2 megawatts for a period of 2 hours or 1 megawatt for 4 hours. It will depend on how we are able to be on the spot at this moment for the power. And the battery system in this case, inverter are able to produce 2 megawatts with near to 4 million kilowatt hours.
So for people wondering, this is Andre Benoit. So he's also working on the project. Surprise. So
He has a...
No, it's that Humber have solar panel on the campus that they use, and it will be charged during the off-peak time from the grid. The grid will charge them when the low rate. Yeah.
Hold on.
I set the peak rates in Ontario many years ago, so I'm not unfamiliar with the arbitrage and the global adjustment. But in terms of sustainability, what goes into battery, how much comes out, what is the microgrid that we just had a presentation on? So yes, Humber's doing a lot, but there's a lot more that can be done, including the building envelopes when you're sizing this system, because we still have lots of waste. I do have a question about the residences.
Can I just respond to the battery? Can I just respond to the question on the battery? Yeah, so we'll charge overnight. It's a bit of a decarbonization play, right? We're very low carbon at night when the base load is all nuclear. So when we discharge during the day, we're offsetting some emissions. But it's essentially a financial play, the batteries. You could carve it out of the project if you wanted to, and we could still do it. It wouldn't have the financial return it currently does, right? So it was a way for us to get the project approved. It was a way, we're essentially trying to be creative to get the economics of the project to work. But you got to think, all this stuff fits together, right? It unlocked so much, right? Because if we're able to reduce our electricity costs, then we can start heating with electricity. And that's going to really decarbonize the campus, right? So it all fits together. It's really, but it's complicated. It's convoluted, right? You have to get. We did, yeah. Yeah, but that didn't go forward for obvious reasons with the emissions.
Awesome. Question at the back.
Thank you. Thank you. Oh, that's okay. Hi, Tanya Massa from Humber College, Office of Research and Innovation, and thanks to the panelists, because I think what you've shared with us is a lot of innovative approaches to big challenges. So a lot of people don't know, but colleges do a lot of applied research. So the question that I have for the panel is, knowing what you know about where we are now, what are some research and innovation areas that you think the college might be able to help you with?
That's a good question.
Let me give you a layman's answer here. So as David said, ASHRAE had a meeting here on Monday that a bunch of the ASHRAE guys here were at. Dragos was involved. And there's a Siemens Smart City Lab on the second floor of the parking garage, which is a pretty cool thing to look at if anybody can get themselves over there. We had the Monday night ASHRAE Toronto chapter meeting. We had a demonstration there before the actual meeting over at the Marriott Hotel. And that's pretty interesting. There's a solar flower out there that you can see that opens up and moves around to try and find the sun and what have you. So yeah, there's neat stuff that you can see here that we've already done in collaboration with Humber.
I'd add a little bit as well, maybe not innovation per se in the technology, but one thing is, you know, as we're adopting heat pumps or refrigeration to move the heat around, from a talent or skill point of view, people are used to working on gas boilers and air conditioning units. And now we're using these air conditioning units as heat pumps and changing the technology a little bit to make them produce hot temperatures so we can achieve projects like here at Humber. But we need the tradespeople and the technicians to be more competent at working on those types of products as well, and that's where we really lack skilled trades in the refrigeration industry, especially as we are, you know, electrifying. That's all going to involve, you know, electric heating, air source heat pumps, water-to-water heat pumps or heat recovery chillers, like what's being used here, and all that needs. You know, the principle of refrigeration is the same in all of them, but the expertise on working on those is slightly different.
Thank you very much to this panel. I'm sure we could continue, but give him a hand. We have a third panel, and that's going to be a controversial one because it's all about innovation, new technologies, and the future. So, we are going to keep Fernando. We're going to keep you, Peter. Max, you're staying. There we go. But we're going to add now Tyler Yorke. Where's Tyler? Tyler. Oh, there we go. So we were talking a second ago about batteries, and Tyler is from Eneon, and they actually bring those batteries here. The battery guy. So we have batteries, we have controls, we have machines, we have design, and we have the person from the city who's in charge of accelerating innovation. So I think it's a pretty good panel. So, as usual, I will start. And, I'll start with Fernando. There you go. What will you believe will be the next innovations that the city will adopt towards decarbonization? What are you focusing on?
Yeah, good question. So, there's many parts of innovation, and you need all of them to work, right? So the one actually, so I'm an engineer, actually, but I've been doing a lot of the business side as well. So I'm kind of a little bit of two minds, right? So one of them actually is business models, and that includes actually the city. So I just share with you actually before the business model that the city chose around wastewater energy, right? When we did actually deep water cooling, the business model was full delivery, right? It was actually invested by the city pension plan owners. It was a city corporation, right? It was all done by the city. So business models are very important. On wastewater, we went to the other extreme. We thought, look, climate emergency, if we're to accelerate, right, then it may be best actually for the city to retain a connection and hosting function, but then actually let the private sector basically take the risk, make the investment, operate and deliver, right? And then maybe very actually apropos to district energy, what we see actually, which is relatively new, party in the industry, is the energy developer, right? So not the real estate developer, but the energy developer. So typically, actually, energy, if you look at it from the one building perspective, right, it's bound, by the real estate development. But once you have, multi-building scenario, either existing or new, right, then it's difficult for the real estate developer to grab their heads around, the energy transition, right? It's much more prone to connect it to gas, do the business as usual, right? So we're seeing energy developers, in Toronto, actually, obviously, Enwave Energy Corporation is based in Toronto. Noventa Energy Partners is based in Toronto. We have Creative Energy from Vancouver, actually very active in Toronto. We have companies like Corix as well, from the West Coast, right? So think about actually that, if that doesn't ring a bell, energy developers, actually that's something really to look into. And of course, when you go on the other side, right, on technology, yeah, there's a lot. We also have a long way to go, which is, working actually on the human capital, right? The equipment, heat pumps, right? Essentially, next generation heat pumps, of every kind, right? Controls and so on. But what I see actually right now, in a sense, to scale, to continue getting the party started in a way, if you will, it's more around the business side, to try to actually have innovative partnerships, innovative business models. When we did our project actually in the lake, where we did the heat exchanger with Lake Geo, we partnered with ecosystems, right? We could have taken a lot more of the scope and not engaged actually with a with a sort of a company that can actually bring all the whole solution, right? But we actually purposely actually thought about what is the business model that will work in this instance. And I'm glad that we were able to actually find a partner that could, put the whole thing together for us, deliver it, do the verification, right, and so on. So that's what I would say. Thanks.
Thank you. So I really had a question for Tyler here. We were talking earlier about batteries, and my conversations in the market, I see batteries now as a tool in the toolbox. It's no longer it's no longer as new as it used to be, but it's still new. And what are the misconceptions that you see, because I'm sure you see a lot of them, with respect to batteries, their use, their implementation? I mean, folks like, I mean, Fernando just mentioned the whole need for anything that you bring to be implementable, usable. There's, you know, it needs to be proven. How do you, what are you seeing? What are those negative things that you see, those misperception, and what are they really?
Tough start for the battery guy.
Yeah.
That's another loaded question, but I think it's important to talk about. So essentially, for context, I'm a manager of technical sales at Eneon Energy Storage, and we're formerly Canadian, now North American-based energy storage integrator. And what that means is we don't necessarily manufacture battery cells, but we put all the major pieces of equipment together and layer on our control system on top to operate and optimize that system. And one thing I think, just to speak to the question, is that with any new or innovative technology, there is going to be risk. And Fernando spoke to it. Typically, that risk is shifted to the private sector. No one wants to be a guinea pig with new technologies. And when new technologies are released, there tends to be, let's say, contrast. There tends to be benefits. But I think more importantly, on my side, there tends to be misconceptions and misunderstanding. And that comes from maybe a lack of education with that particular technology or a lack of demonstration. So for us as integrators, you know, the way we prove these use cases is by projects. And in the early days, I mean, we've been integrating for, well, 10 years now. We started in 2013. And those early systems were microgrid systems for northern remote communities that were trying to achieve diesel abatement. And, you know, it's a proven use case, but people start to ask, well, how does that translate? You know, I can't prove the same use case for diesel abatement at Humber College, but I think there may be a play here. So we start to look at it holistically. If we take a campus, for instance, and we look at electrification, then all of a sudden it starts to make sense to have means of peak shaving. So battery energy storage in general, there may be other controversies or negativity around safety, but I can assure you that batteries are certified to certain standards that specify certain requirements around safety. So if there's any interest in battery energy storage after, happy to field questions about what that looks like and how that's evolving both in Canada and the US.
Thank you very much. Can you hear me?
Perfect. I'm not sure I need the microphone, but I guess a question for Fernando. Do you see that there is, for City of Toronto, like a common form of sharing data or storage of data to be accessed? And where I'm going with this question is on the building automation side, you know, we've got Modbus and BACnet. EV systems are running OCPP. We've got RESTful APIs, and we have all these little empires that are all technically open, but none of them talk and communicate together. Are we moving towards a standard where all of that will be in a common format so then we could access it and we could actually see what the batteries are doing versus the HVAC system versus the, you know, heat recovery systems versus the power meters, so that it would all be common form and then we could actually draw conclusions in between?
No, thank you for that question, actually. It's an excellent question. And, you know, maybe I'll start by saying that the city actually wears, you know, several hats, right, as you can imagine, kind of like the college, right, in a sense. So we have, you know, a more traditional role, actually, in terms of our facilities, and we do grapple with that, right? So currently, actually, we are doing basically a standard because we have about 50 new community centers on the books, you know, for the next, for the 10-year capital. And we don't want to have you know, that situation, right? So that's more of as an owner to figure out actually, you know, some standards around that. The other hat that we wear actually, which you know, you touched on your question actually, is now as a regulator, right, for new development. We have a building performance standard, you know, coming out you know, later in the year, which will regulate existing buildings, right? And there, our role actually changed a little bit because we're not actually in the business of specifying solutions, but we're in the business actually of you know, demanding standards and raising the standards, right? Maybe last thing I'll say actually is that we do have an open data portal, and we make a lot of data actually available. We believe that it is actually our duty as a taxpayer-supported, you know, organization. So if you go to an open data portal, Google it, you'll see actually a good number of data sets. But if there's a data set that you want that it's not there, a request actually helps to work actually with our open data team. So we have things like, you can see all the building permits, you can see actually all the development permits, you can see all the cities, installations of renewable energy, and on, right? But I think, to your question, actually, we need to be a little more transparent. And again, if this is data set, that you want, either for research or from an industry perspective, I will encourage you actually to request that data. And then we tend to almost always, make it available. Thanks for the question. Right.
So Siemens has come out with something called Accelerator, Building X. It used to be called Building Twitter. Joke. We had it first, but I suggest that if you're interested in this, just Google it, right? And it'll lead you to a whole bunch of things. It's integration of, BACnet, Modbus, but also a lot of other things too. And it's also about providing a platform for other companies to develop their products that will be compatible with this, so all of these things can talk together. I think it's where you're getting to, right? So that's a takeaway. I can't give you a real dissertation on what it is, but I can tell you to look it up on the internet. Accelerator, which starts with an X, marketing, and Building X. And this is what you're talking about, I think.
That's. Oh.
This is a session about district energy, which is more about thermal energy than it is about electrical energy. And one of the really nice things about thermal energy is that it's relatively inexpensive to store. Maybe less than 1/100th of the cost of per energy unit of electrical energy. And I wonder if in talking about innovations in district energy, I wonder if the panel could talk about the role of storage, even seasonal storage, which is entirely possible with thermal energy, but is not possible with electrical energy because of the cost.
One quickly myself, just because I looked at something on the internet before I came down here. There are these huge friggin' tanks under the well. Do you know about this? Yeah, so this is all controlled by Siemens PLCs. They had to develop a special fiber optic temperature sensor that would measure the temperature at, every meter or whatever through the depth of this tank. But I think that's exactly what you're talking about. It's storing energy just using water, not batteries, right? Okay.
It could be other media like liquid sodium or something like that, but it's basically water.
It's something that we're looking in some of our project, but so far we haven't been successful into integrate it in a economical way. Even though it's cheaper, you can have a big tank or stuff like that. And I think the only way we succeeded in integrated it is with the geothermal field, which is a form of thermal storage. So we've done a lot of that. Mostly in the Quebec province. So that's the way we're using it so far. Yeah.
Yeah, but maybe I'll add to that actually, and it's a really good question, Richard. And Peter, so again, I go back to the business case, right? So the technology is one thing, it's been around forever. The question actually is what makes it be valuable, right? So in the case that Peter mentioned actually about I think it's 2 million gallons of water stored underground for this new development. And the business case was around the fact that we were expanding deep water cooling, but the timing was going to be off. Okay, so either the development could actually go traditional and not do renewable energy, or it had to be delayed by 5 years, right? So we have 2 instances actually of basically peak forming, not peak shaving, right? Of storing cold water for the well. It's a massive tank. But we also had actually another building, 18 Yorke, that did this as well for the same idea. So we always have to look at, again, I just encourage you to actually look at issues, from more than one dimension. The technology is around, the cost is, not expensive. Although I would say that the cost, the monetary cost and the capital cost is low compared to electricity, but they have a huge footprint, right? So looking at it from those two angles, that's how we have a couple of examples actually in Toronto of doing that. Maybe another thing related to that actually is that when we did actually our work with Toronto Water on the wastewater side, and we're trying to recover also heat and reject heat to the drinking water side on the reservoirs and so on, we noticed actually that any water system in a city actually has a tremendous amount of storage, right? And the function of that storage actually is to be able to actually make the peak for the morning showers, actually in the evening dinners, right? And it was shocking that if you were to remove all that storage in the water system, the capacity of the water system had to be 3 to 5 times bigger. So consider that, right? So if we didn't have actually storage in reservoirs or tanks in our water systems, in order for us to shower in the morning and have dinner in the evening, the pumps and the pipes had to be 3 to 5 times bigger. And in a way, actually, that's the challenge that we have, or the opportunity for the thermal systems, right? As well as the electrical system, that we've had 120 years of electricity, and barely now, actually, we're getting to economic local storage of electricity, right? So consider, actually, that when you're reading, actually, the paper in the morning or on the internet, and you hear these stories, actually, about, the energy transition, actually, will require 2 to 3 times more energy. Do some critical thinking on that, because it will require 2 to 3 times more kilowatt hours, right? But by using storage, right, you can get 3 to 5 times more energy out of your system without actually having to increase the capacity necessarily. So hopefully that's helpful.
Yeah, I think you mentioned geothermal is a traditional way of thermal storage. Another one that we haven't mentioned, not widely adopted, is ice storage as well. So there's systems where you'd freeze tanks of ice, and then they would melt so that you could, run your HVAC system on off-peak hours to save, your electricity. And to add to that, we're now using the ice. People think ice is cold. You're going to use it for your cooling system, but it can actually be used for thermal storage for a heating system, where we can use that on the source side, freeze and thaw ice, and then upgrade that heat with a heat pump. So now it can be used, we thought of it as a chiller kind of cooling system, but now we can use it for decarbonization and kind of get more of an average load to have all the benefits of storage as well on your heating system. So that's kind of a new thing that's being worked on.
Question on ground source technology. Like, what are your experiences, or where do you see and challenges around it? Like, anyone that wants to.
Sure, I can speak to that. Yeah, heat pumps are using ground source all the time. When they get older, they're prone to leaks. Even sometimes when they're new, they're prone to leaks. So that's always, a mechanical issue. We did another job here, and it was kind of similar to how we're talking about controls, how the heat pumps have to coexist with gas boilers potentially. Well, the gas boiler was sized for make 160 degree hot water. The heat pump was sized for 140. So the heat pump's never going to run, and that's it's a brand new building. So even today, I don't think we're are not doing a geothermal is not an off-the-shelf design. So we hope back to my other thing is we need skilled people to work on the machines, but also we have to be more familiar. We'll work on geothermal ice storage, integrating batteries or whatever else it is. So, overall, geothermal has been used for many, many decades in Ontario. Many schools have them, and I think the last hurdle for that geothermal is the cost to install, especially in urban centers. That's why I think air source heat pumps are perhaps becoming slightly more popular. The efficiency is slightly less, but you can implement them where geothermal is maybe more problematic. And in fact, we've implemented them where we've used a hybrid where you have some air source heating and geothermal coexisting. The geothermal acts more like a thermal storage, and the air source, acts, during when it's needed. And that way you can run your air source units flat out all the time, so you get your maximum return on investment on those, and you supplement with your geothermal. So there's, all kinds of tricks you can do like that.
Can talk about a job that I was involved with years ago. I won't tell you what the job is, but I think it's hard to design a geothermal field, right? You're sort of guessing, how much heat's in the ground. So we had this building, and it just had water circulating for the heat pumps inside the building, and it didn't have a gas boiler like you're talking about. And then the ground got to like March and went, I got nothing. And so all the heat pumps in the building, they kept wanting to suck heat out of the building, and the loop got colder, and it started to turn into like a Dairy Queen Mr. Misty. And yeah, that can happen, right? So I think the first year of a geothermal job must be the stressful year, right? To see what do you actually have. And this job was designed a while ago. There's probably better models than that now. But I don't think it's an easy thing to figure out how much heat you're actually going to get out of the ground, right?
Maybe a lot actually. So thanks for that actually. Maybe to bring it back to district energy, right? The challenges actually are greater when you're doing an in-building system. You're an island. You're not connected actually to anybody else, right? And you're on your own. So a lot of the issues actually are performance. It could be actually balancing the summer versus the winter. Remember that geothermal, meaning geo-exchange, like shallow, right? It's just a battery. Like you're not really getting direct use energy, like deep if you were to go a kilometer down, right? So what I would argue actually that for geo-exchange to succeed actually in scale, you need a couple of different things. One of them actually is it's best done actually in a district energy scenario, even if it's a small system, because you're sharing, you can base load, and you have a little more flexibility. And by the way, you have actually a business model where there's an operator that can actually balance all that out, and it's not a homeowner or a condominium that has to actually figure this out, it's not within their wheelhouse, it's not within their expertise, right? And then maybe the other side actually would be, how does it scale, right? So you may have actually seen that Enbridge, now has a non-regulated arm called Sustained. And, I have not seen projects yet, but my understanding actually talking to them actually is that they want to get heavily into the geothermal, geo-exchange, business. And we've seen companies in the US like Dandelion that have reinvented geo-exchange. So, much more compact, drilling rigs, smaller actually diameter, boreholes, right? And then, one company doing the entire scope. You don't have to bring, a driller, mechanical contractor, and, So again, in terms of actually, we have a very tiny geo-exchange industry. It's never scaled. But I think actually it's got a lot of potential, meaning because you can do geo-exchange everywhere. You cannot do sewer anywhere. You have to be close to a sewer. You cannot do lake water everywhere. You have to be close to a lake. But geo-exchange actually has that potential that can be developed pretty much anywhere. But I'm really looking forward to actually that technology really scaling from a cost perspective. To have a big company like Enbridge maybe to sort of take this on could really actually change the economics and the broad applicability of geo-exchange.
So it's a great layup, because my next question is, we have all those technologies and they're being integrated, and one is supplementing the other, and there's a basis of a district energy, and we're trying to recover heat, and at the same time we're getting a battery. We're trying everything to get closer to that net zero. How close are we? And of course we can do all those technologies, but like you just mentioned, there's economics at play. How are we close from an economics perspective that we can get it done? Anybody? Especially the people who are positive about this answer.
Maybe I can start actually from, again, the city perspective in the sense that we have the plan, right? The plan actually is to get to net zero by 2040, right? So if the question is, how are we doing broadly, like the royal we? How are we doing? Well, first of all, it's not going to be a linear, because if it is, actually, we're not doing well. But we don't expect it to be linear, hopefully, right? Hopefully it'll be more of a hockey stick, right? And it's the proverbial, actually, S-curve, right, of technology, where you start very slow and it's a slog to get to the 1, 2, 4, 5%. But to your point of economics, right? This is not going to happen unless we figure out the economics, right? So the S-curves, all the study, all the research, the literature around transitions, be it from a flip phone, to a smartphone, be it from no electricity to electricity, being from, the horse to the car, right? Behaves in an S-curve. And the theory, actually, at least, which I think is going to hold true, actually, for the energy transition, right, is such that not only we need to figure out the economics, because we need to figure out the economics, but we will not scale if the economics are not there. We're going to be stuck, actually, in the 5% box, right? So in a way, actually, it's kind of good news and bad news, right? People worry about the government mandates are going to bankrupt everybody, right? And I need to remind folks that, hey, we've got the plan, actually, we're trying to align action. We're trying to say, federally, by 2035, 100% of vehicles are going to be, zero emissions. We're trying to say in Toronto, by 2028, 100% of development will be zero emissions, right? We're trying to say, essentially, we're trying to basically, as an impartial actor, hopefully, say, look, we need to transition, actually, so why don't we agree, all of us, the entire, actually, sort of ecosystem, right? No pun intended. Or intended as well, ecosystems included. You're part of you're a big part of the industry. So everybody needs to actually pull together to do that. Now, are we going to get there by 2030 or 2028, 2032? Actually, I really don't care. As long as, right, we get out of the 5% box, we figure out the economics, around actually how to multiply and scale, right? And then we know actually that we're in the journey, right? So hopefully that helps frame the. But it's gonna be tough. But at the same time, actually, maybe to the young people actually in the audience here, actually, is a huge opportunity, right? Because we need to actually basically change everything, right? So it's not an incremental, endeavor. It's going to be a step change, transformational endeavor. So it's going to be a huge opportunity, economically, career-wise, for those that choose to actually ride that wave.
It's just in our lifestyle also.
Yes, absolutely. Well, yeah, for sure. Like, so when we do our climate planning, actually, a bunch of energy geeks here, I'm sure. We're all energy geeks. But what we try to make actually pretty clear, actually, right, is it's going to be a better future in many ways, right? It's going to be quieter, right? It's going to be actually, the air is going to be cleaner, right? There will be actually, an economic development opportunity for young people, right? So it's a really good point. It's more of a broad base, not just about carbon.
So, SF, I think we're pretty far from the net zero you were talking about, and I was pretty pessimistic a few years ago about the way we can get there altogether. But I think the COVID crisis show us or show me that when we all think the same way and when we all align on one objective, we can turn around quite quickly. And I think this is what we need, and this is probably the hockey stick that you're talking about. Like right now we're kind of building our knowledge, our common understanding on global changes and stuff like that. And at one point we'll all align and we'll take on that crisis.
I love that optimism and the spirit, because motivation will get it done. And also to what Fernando said, this is a great opportunity for the younger member of our crowds who's going to lead us forward. And the next session, right after this panel, is an opportunity to network. So I hope you all brought your resumes. I know I dusted off mine and I laminated it, and it's ready to go. But I really want to thank this panel, and please stay around. Let's talk. Let's exchange ideas. Let's enjoy the rest of the evening. Thank you so much.